In this section, we will discuss linearization and differentials. Let's start with linearization. So here's the idea. The idea of linearization is that we're just simply going to approximate a complicated function using a tangent line. So again, the ideas we're going to be discussing first are concerning approximation. And this is a part of calculus that is sometimes referred to as numerical calculus, where we're not going to be focusing so much on finding a derivative, but we're going to be finding approximations of certain functions. Again, approximations are useful because sometimes we just want something easier to calculate if we're dealing with something astronomical. So here's the idea. So let's go ahead and look at this function y equals x squared. So of course, that has the shape of a parabola. And if you were to look at that in a computer window or a graphing calculator window, you would have a pretty good idea of what it looks like. Now, linearization is we're going to be looking for a line. So of course, we want to be using the tangent lines. And again, at each point, you could find a tangent line. So you can see right here, for y equals x squared, we can find the tangent line y equals 2x minus 1 at the point 1, 1. So of course, if we zoomed in, you can see in the second window, it's a little bit harder to tell that this is a parabola because we've lost some information. And then in the bottom two windows, look what's happening. Essentially, we're zooming in so close that you can barely tell there's two graphs here. And then if we're looking at here in orders of magnitudes of tens, hundred thousandths place, you can really see they're essentially going to be the same value if we're looking at values near 1. So you can see we're only 0.003 to the left or 0.003 to the right. So here's the idea. If f is a differentiable function at x equals a, we can obtain the approximating function L of x by simply noticing the following few things. So let's go ahead and kind of look at what it is to be a line. And if we were to start with just lines, we just simply have that at a point we have y minus some given y naught is equal to m times x minus x naught. Now, in terms of functions, y naught is simply the output at x equals a, and the x naught is simply the x value that we are given. So the linearization of this is, well, let's go in and consider what was m in terms of derivatives. M was just simply f prime of x and then evaluated at a. So in other words, our linearization is just going to be built off of this point slope form. And of course, we can go ahead and solve this for y. And that is to say, we would have the f prime at a is our m. X, in this case, is just going to be x minus a, because again, that's just coming from right here. And then lastly, we have our y-intercept. Well, that's just going to be plus f of a. And again, y-intercept, and that's what we're getting from right here just by adding it to both sides. So what we have found is that this function L of x is what we call the linearization of f at a. The approximation f of x is approximately equal to L of x of f by L is the standard linear approximation of f at a. And the point x equals a is simply referred to as the center of the approximation. The farther you get away from the center, the less accurate this approximation will become. And there's several other ways to approximate functions, but that will be discussed in Calculus 2. Let's go ahead and find the approximating function. That's to say, we need to find the linearization of a function f of x equals to the square root of 1 plus x at x equals 0. And then we'll go ahead and compare the values of the approximating function with that of the original function. And again, this is going to be really nice if you ever needed to kind of calculate something modeled by the square root of 1 plus x, Because again, the square root of 1 plus x introduces a lot of errors just because for non-perfect squares, it's an irrational number. So let's go ahead and start with our linearization. That is to say, L of x is our linearization. And that formula from the last page, and by the way, typically we'll write f of a first because that's our center for our approximating function. So then we need to add to that f prime of a, and we're going to multiply that by x minus a. So let's go ahead and get this information. We were given that x is equal to 0, so to find f of a, we just simply have to plug in 0. And when our a this time is 0. So when I do that, I'm going to plug this in. I get 1 plus 0, which is the square root of 1, which is just equal to 1. Now, let's go ahead and get the other information. So we're going to need f prime of a. So of course, we can go ahead and actually find the derivative right here. So f prime of x is going to be 1 over 2 square root of 1 plus x, and you can easily verify that by just using the power rule. So that is to say f prime of 0 is just going to be 1/2. Now, we have all the information we need. Let's get our linearization. Our linearization, L of x, is equal to f of a, which we found is 1. And then we go ahead and add to that f prime of a, or at a, so that's going to be 1/2. And then we're going to do x minus our center. In this case, our center was just going to be 0. So we found our approximating function is just going to be 1 plus x over 2. Now, how good of approximation is this? So again, you can go ahead and verify this for a few values. But let's go ahead and just kind of take, let's say we have some input x's, and let's say we'll do, let's do something close to our center. So let's do 0.2, and let's go ahead and see how that plays out. So if I plug that in, into my linearization, I get 0.2 evaluated in here. And when you go ahead and work this out, you're going to get 1 plus 0.2 over 2. And you can go ahead and verify this as well, but that's a work out to approximately 1.1. And you'll see in the next step, let's go ahead and just realize that that's going to be 0 there. Now let's go ahead and do that in our original function. So f of x, that is the square root of 1 plus x. If we evaluated that here, we would get the square root of 1 plus 0.02, which is equal to the square root of 1.2. So back that up, 1.2. And if you were to type this in, this is 1.0954. And of course, this is irrational, so this is going to continue on forever. So you can see our epsilon, our error, is actually pretty good there. We're off not even a tenth, about 0.46. But again, let's go ahead and take an x value that's a little bit farther away. So what if we were to go ahead and consider this at like, let's go and consider 8, so that comes out to be a perfect square. So if we let x equal 8 and we plug this into our linearization, that is to say L of 8, we would have 1 plus 8 over 2, which is 5. And then if we were to actually evaluate 8 in our original function, we would have the square root of 9, which is equal to 3. So you can see our epsilon, our error, is getting pretty bad as we move away from our center. Let's go ahead and look at another example. So you can see down here, we're asked to find the linearization of f of x equals to cosine of x at the center x equals pi over 2. I would encourage you to go ahead and pause the video and try that out before hearing the solution. All right, let's go ahead and look at how to find the linearization. So just like last time, we have to just go ahead and I'm going to write our formula, or our approximating function here, just as we get used to it. That is L of x is equal to f evaluated at a plus f prime of evaluated at a. And then we have x minus a. And again, this is a function of x because our x right here is right here inside the parentheses. So let's see what we need, f prime at a. Well, this time a is equal to pi over 2. So if I'm going to evaluate my function, f at pi over 2, that will give me my f of a that I need. So cosine at pi over 2. Well, that actually works out pretty nice. Cosine at pi over 2, the top of the unit circle, the x value is 0. Now, of course, f prime at a, we're going to need f prime of x in order to get that. So the derivative of cosine is just minus sine of x. So when I evaluate pi over 2 in our derivative, we get negative sine of pi over 2. And in this case, we're going to get minus 1. Now, L of x, we have the information we need. The linearization is going to be f of a, which is minus 1, plus our, let's try that again. That isn't quite right. F of a is not minus 1, it is 0. And then we add to that the linearization part. So there's the derivative evaluated at 1. And then we're going to have x minus pi over 2. Simplifying, it's just going to be minus x minus pi over 2. And distributing that negative, we get minus x plus pi over 2. And you can see over here on the right in red, we do indeed have this linearization. And you can see as we're looking at values somewhere around pi over 2 plus or minus pi over 4 is a pretty good approximating function, but that quickly becomes a very poor approximation as we move away from pi over 2. The next topic we will be looking at is called differentials. And we really actually have quite a bit of understanding about the intuition and how to compute these. So we may use Leibniz notation dy dx to represent the derivative of y with respect to x. We've been doing that for several weeks now. But what I did stress earlier is that this is not necessarily a ratio. This is an operation telling us to find the derivative of y with respect to x. But we could go ahead and consider this in the context of a numerical calculus and the fact that we can have some variables with properties that when their ratio actually exists, it is actually the derivative. So again, typically this is going to be in a numerical context. So let's go ahead and define what these new variables are. And just like x and y, one will be independent, one will be dependent. So let y equal f of x be a differentiable function. The differential, so we're defining our differential. And the first one we'll call dx. This is the independent variable, which makes sense because x is our independent variable, one concerning xy. And then what we have is a dependent one. That is to say, we have another differential, and we'll call that dy, and it's simply defined as stated above, that when the ratio of these exists is equal to the derivative. So this dy, this variable, is going to be the derivative multiplied by dx. And again, what this is really going to be giving us a way to understand is how one small change in x relates to a small change in y. Again, d representing the difference. All right, so let's go ahead and first of all just figure out how to compute these. So example 2, we're going to be finding differentials. So in the first example, we're asked to find dy if y is equal to x to the fifth plus 37x. And find the value of dy when x is equal to 1 and dx is equal to 0.2. Again, this is kind of a numerical approach we're taking to understanding a small change in x. How does it affect a small change in y? So how do we find this? Well, if the ratio exists, it's equal to the derivative, so we need the derivative. And so if we're thinking, okay, the derivative dy in terms of its definition was equal to f prime of x times dx. In other words, dy is equal to f prime of x, which is 5x to the fourth plus 37 times dx. I mean, you really can think if dx is a a variable, divide both sides by dx, and you have dy dx, just like we've been used to dealing with. And typically we'll just find dy dx and then multiply by dx to get the differential dy, and we'll see that down below. Of course, well, if we kind of consider this numerically, this is just going to be 5 times 1, because x is given to be 1, to the 4th plus 37 times 0.2. And what does that compute out to? If you go ahead and you can verify this, works out to about 8.4. So a small change in x, just a small change, such as like, what do we have here, 0.02. If you change x by just 0.02, you're going to change the dy by the y values by 8, and which makes sense if you look at the x to the 5th. That is going to cause a big change in the x values. And again, just to verify this, what you could go ahead and do, I encourage you to do this as a little bit of an exercise. Go ahead, and if we have f of x is equal to x to the 5th plus 37x, go ahead and plug in 1 and plug in 1.2. And we can go, let's go ahead and do this actually, just to. So when we go ahead and compute these two values, let's see what we get. So when we plug in 1, we get 1 plus 37, which is 38. And then I just did this off to the side. When we plug in 1.2, we get 46.88. So if we look at these two values, they differ a little bit. So I need to check my calculations. Hold on. Thanks for holding. So again, if we look at the difference between these two, it's a little bit more than 8.4. It's approximately 8.8. And again, keep in mind that this is all centered around x equals 1. So again, I went ahead and did another computation off to the side, and what I found, if I compared f of 1.1, and I found the difference between f of 0.9, the difference between those two is approximately 8.42. So you could even see that's a better approximation when I let d of x differ by only 0.2, and my approximations are around x equals 1. So now that we've kind of have a way to compute these and just some basic understanding on what it means from a computational standpoint, let's go ahead and do a few more examples, and then on the next slide we'll go ahead and look at how to understand it geometrically, so using graphs. So here's two examples. In the case of B and C, we're going to have to go ahead and use, in the case of B, the implicit differentiation. In the case of C, we'll have to use our logarithmic rules. So I would encourage you to go ahead and pause the video here and try that. All right, let's go ahead and look at the solutions together. So again, keeping in mind that essentially we're going to need to take the derivative to find the differentials, let's go ahead and take the derivative of each side of this separately. So that is to say, if I apply the sum rule, I just need to take the derivative of xy squared with respect to x minus the derivative of 4x to the 3/2 minus the derivative with respect to x of y, and of course the derivative of 0 is 0, so nothing really to worry about there. So on this first one, I'm going to need to use the product rule. So first times the derivative of second is 2y, and then because our derivative is with respect to x, I need to multiply by dy dx, plus the second, which is y squared, times the derivative of x is 1. So that first derivative is now taken care of. Second one's just a straightforward power rule. So 4 times 3/2 subtract by 1 gives me x to the 1/2. And the derivative of y is 1 times dy dx. And now let's solve for dy dx. And then after that, we'll multiply both sides by dx. So let's clean this up. So let's see, we have 2xy dy dx. We also have a minus dy dx. And then let's move to the other side, the other terms. So we have in this term right here, we're going to divide by 2. So that gives me 6 square root of x when I move it to the right side with the 0. Then I subtract by y squared. On the next step, I'm going to factor out this common dy dx, much like we learned when we were taking implicit derivatives. So that leaves me with 2xy minus 1. I'm going to finish this computation over here. Now, let's go ahead and finish writing that first. So let's bring this down just for completion. So this would be 6 square root of x minus y squared. And now I'll finish this computation up here. By dividing both sides by the 2x minus 1, I find that 6 square root of x minus y divided by the 2x y minus 1 is what dy dx is equal to. And again, now thinking about dy and dx in terms of differentials, by multiplying both sides by dy or by the dx, I find that dy is equal to 6 times the square root of x minus y squared, all divided by 2xy minus 1 times dx. Now, in the case of c, we have just a chain rule that we should be considering. So dy dx, taking the derivative, 5 is constant multiple rule. Leave that out in front. The derivative of ln of x, do recall that the derivative with respect to x of ln of x is 1 over x times the derivative of what was in the bottom. So that was the application of the chain rule. Of course, no composition there, so didn't need it there, but here I will. So that gives me 1 over 2 plus x cubed, leaving the inside alone, times the derivative of 2 plus x cubed prime. Now, this is just going to give me, let's see, the derivative of 2 plus x cubed is 3x squared. So on top, I have 15x squared. On the bottom, I have 2 plus x cubed. So that is what dy dx is equal to. And by multiplying both sides by dx, I find the differential dy is equal to 15x squared over 15 plus x, or 2 plus x cubed times dx. Let's understand what differentials are from a geometric standpoint. Again, they're really just measuring change. So we have a couple of different cases of change going on. So you can see here we have delta y. Delta y is simply the change in the y value. So you can see that is, if you look at the change in the y values, f of a, that goes up to here, which is f of b, or really just a plus the change in x, evaluated in the function. Then we have the linearization. Again, this linearization is just essentially the tangent line. So you can see the idea right here. Or more specifically, I should say the tangent line at some x value given to you. And then you have your differential dx, which is just the change in x, and that's what we're varying over. So what we can go ahead and do is just use these ideas and estimate different changes. So you can see down here in this example below, we are asked to go ahead and find various approximations, different differentials, and etc. And it's really pretty straightforward to compute these. If you look at this, we're given x is equal, or x naught equals to 2, so this is our a, and we're given our differential 0.1. So to find the change in f, and again, just remember the change in f is just the change in the function, so the change in the y values. So what that is, if we're looking at up above, we're really just computing this value right here. And that's just as easy as saying, okay, what is my initial x value? That was 0.2, and I add to that 0.1, and then I subtract from that f of negative 2. In other words, I'm just going to find, let's see, that would be negative 1.9 minus f of negative 2, and that's straightforward to compute. Then, in the case of b, we're asked to estimate the differential of f, or again, this is just dy. So we're just going to go ahead and find the derivative. So we're going to find f prime of x, and let me go ahead and write that a little bit neater. So in other words, df is just going to be dy, which is equal to, and not to be fused with delta y. That's just not anything involved with derivatives there. So we would have f prime of -2 times 0.1. Again, very, very straightforward to compute. And if we're looking at that in the terms of our what's going on up here, where is the change in the function? So let's go ahead and slide back up to the top. And well, where is our dy? Well, the corresponding, if we're looking at this, what this is saying right here, the dx is a small change in x. The corresponding change in the linearization is precisely dy. So what does that mean? Well, look at this. Delta L is equal to f prime of a dx. In other words, it's just a notational thing. This is just another way of finding the differential y. So this is what we computed in b, and then we had already figured a right there. Then the last thing we have to go ahead and look at, let's go ahead and slide back down here, is we need to find the approximation error. That is to say the difference in these two values. So in other words, if we're looking at the difference, let's see, we had, let's go ahead and just notate this in red. There's B, there's A. So that is to say the difference in these is C. That is the error between the linearization, the tangent line, the derivative, etc., and the actual function value we can evaluate in A. So in other words, to go ahead and compute this from a numerical standpoint, we're essentially just going to be taking what we found in A. So we have A right here, and I'm going to keep this color-coded. So in other words, A was in blue, and then we have to subtract from that what we find in B, and the error is just the absolute value of it. So there is our geometric understanding of differentials.